Video explains the problem 351. So here's the first thing is to mark your control volume. So I will take this region of fluid as our control volume. And then I will take that part out from the isolate that part to the for more clarity. So that's the fluid domain. And then the bucket is moving. So this control volume is a moving control volume because this bucket is moving towards that direction. And given the radius of the disc is r, radius is r. Let's say this is radius r, and then linear velocity is r omega or omega r. And then the jet velocity here is Vj. And we take that, let's say this is cross section 1 and this is cross section 2, where flow enters at cross section 1 and leaves at cross section 2. And we'll take Vj, V1 is equal to V1 jet velocity, that is with respect to Earth, is equal to Vj, and V control volume with respect to Earth is let's say Vb, which is equal to V bucket which is omega r Vb. And then we consider that V2 as our velocity at section 2, which we take it as the velocity with respect to the control volume. So let's take velocity at 2 with respect to the control volume, V2. This is something that we take or assume at the beginning. So now we can what we need to do is to apply the force or the linear momentum equation. So we need to find this force F, let's say Fx. So we're gonna apply the linear momentum equation. Linear momentum equation under steady equation in x direction. So in the x direction, okay. So we can write sigma F is equal to d over dt control volume rho velocity v dv volume and then plus control surface rho v dot n dA. Now under steady incompressible flow with so this should be moving control volume VR, right? The moving control volume, and then this should also be VR, and this is VR2. For steady incompressible flow, for a steady incompressible flow, we can write sigma F is equal to this term right here. This term right here is 0. That term right here is 0. So we can write control surface rho can be taken out. VR dot in dA. So we need to find the relative velocity at cross section 1 and cross section 2 relative to the control volume. So we'll go on the sidebar. So we want to find cross section 1 relative to control volume, which is equal to V1 relative to Earth plus VE relative to control volume. So that is actually V1E minus VCVE, which is VB. So this is VJ minus VB, right? VJ minus VB. And then we can also find V2CV is V2, which we actually assumed at the beginning. Now, to find V2 in terms of VJ and VB, which are the ones that we already know, because we don't know what V2 is, we need to apply mass conservation. For mass conservation, steady and incompressible flow, we can write control surface VR dot n dA equal to 0. So at cross section 1, at the cross section 1 we can write cross section 1 we can write VR is VJ, which is towards the control volume, but the normal vector is outwards on the control volume, right? So then this is going to be we write the equations with respect to the control volume, right? With respect to the control volume. So that's going to be a negative VJ minus VB dA plus at the cross section 2 unit outward normal vector and velocity both in the same direction. So this is going to be just V2 dA. And both of these velocities are Vj minus Vb and V2 are uniform velocities, under assumption uniform velocities. Then it's going to be negative Vj minus Vb Aj should be equal to plus V2 equal to 0. So we can get V2 is equal to Vj minus Vb. We need that. And then, so let's take this as our equation 2, and this is 1. So I'm going to use that in this equation. So there's no pressure forces acting on it, because hydrostatic pressure forces are neglected because they are the same all around the control volume. So we can neglect that uniform pressure because the pressure is equivalent to the atmospheric pressure. So atmospheric pressure is the only pressure that exerts a hydrostatic pressure on this region. So we can neglect that. So we can write our equation. First equation, we can write negative F of x, that's the force acting on the bucket, equals to rho, the relative velocity in the x direction, for the cross section 1. So for the cross section 1, it's going to be Vj minus Vb, that's the relative velocity, and Vj minus Vb is in invert direction, or in the direction, this direction, right? Because Vj in that direction, Vb, negative Vb also in that direction. So that is the direction. So we can write this in terms of Vj minus Vb times negative Vj minus Vb, right? And then at cross section 2, it's V2 times V2, right? V2 times V2, this is positive V2, dA. So there's a dA here as well, dA. So considering those are uniform velocities, because we get rho negative Vj negative Vj minus Vb squared Aj plus V2 is the relative velocity in the same direction. Okay, so this one should be negative because direction is in this direction, so that's a negative V2. So you get negative Vj minus Vb times Vj minus Vb. The first Vr in this equation for the second cross section should be negative, and then you have a rho should be in front of it, rho Vj minus Vb and Aj. So we get negative 2 times rho Vj minus Vb squared Aj. So that's Fx. So Fs equal to 2 times rho Vj minus Vb squared Aj. So Vb is omega r. So we have 2 rho Vj minus omega r squared Aj. So the next question is what angular velocity is the maximum power delivered? So power is Vb times Fx. So we can find the power Vb is omega r. So we can write 2 rho omega r Vj minus omega r squared Aj. So maximum, to find the maximum power, you find dp over dx, and should be equal to 0 at maximum power, maximum or minimum power, okay? And we find dp, dp over d omega. So dp over d omega is equal to 2 rho r are constants. Aj is also constant. And we can write this one dp d over d omega times Vj minus omega r squared, right? So that's the function that we need to derivate. Find the derivative of omega r Aj. So we can write Vj minus omega r squared d over d omega plus omega times d over d omega Vj minus omega r squared. And then you have 2 rho r aj vj minus omega r squared, this equal to 1 times 1 plus we can write omega 2 times vj minus omega r, right? And then derivate the function inside, so it's going to be 0 minus r. Okay, and then we have 2 times rho r a j, we have vj omega r squared minus 2 times r omega vj minus omega r. Vj minus omega r is a common factor for these two. It's a common factor here. So we can take that term out. 2 rho r a j vj minus omega r. And you can take this as vj minus omega r minus 2 times r omega. So we have 2 rho r aj vj minus omega r, vj minus omega r. This is vj minus 3 omega r. Okay, and now when you set, this is dp over d omega. When you set dp d omega to 0, you get maximum and minimum values of omega. When you set that to equal 0, vj minus omega r times vj minus 3 omega r equal to 0. Okay, equal to 0. So from that we get omega is equal to vj over r, or omega is equal to vj over 3r, right? So if you apply vj over r for omega, the power equation, this equation right here, if you apply vj over r for this equation, this term is going to be 0. That means power is going to be 0. So minimum power is at this value. So this gives you the minimum. So this gives you the minimum, corresponds to the minimum. So that gives you, this corresponds to the maximum. So that therefore omega is equal to vj over 3r when p is maximum. Now by substituting omega equals vj over 3r, we can find maximum p. So p max is equal to 2 rho instead of 2 rho omega r, so you can put vj over 3r times aj, and here as well we can put vj minus omega r. Omega is vj over 3r times r squared. So we can cancel r to r here as well. So we have 2 rho vj aj over 3 times, this is 2/3, so we have 2 vj over 3 squared. So we can write 4 vj squared over 9. So 9 times 3 is 27. 27, and a 4 times 2 is 8 rho vj cube aj. So that's maximum power. And if they have a lot of blades, many blades, what would happen is this voltage jet strikes on uh, a blade at all the time, it's like if you kind of blinking your eyes, you will see that at that the same frequency. If you can put a kind of a stroboscope or something like that, you can see that this bucket is a stationary when you have a lot of buckets circling around. So that means your mass flow rate does not affect, it is not affected by the velocity of the control volume or moving bucket. So we can write that mass flow rate mj, mass flow rate m dot is equal to rho aj vj. So therefore, by taking that into account, we can write f or p. If there are many buckets, p is equal to 2 rho omega r aj rho aj vj, and then for momentum we still consider vj minus omega r. So if there were many buckets, we can write a power is equal to 2 times rho omega r aj vj minus omega r. So that's if you have a number of many buckets, the power is equal to that.